a comprehensive overview of fluids in metamorphic rocks is just sort of beyond the scope of the time we've got available to us. And not only do we not have sufficient time, we probably need to bring in a larger cohort of colleagues to work on that. But we've had questions throughout the week along the lines of, all of the diagrams you're showing, or most of the diagrams you're showing, use water as the fluid. What about water CO2 fluids? What about more complex fluids than that? And so, although we're not going to be able to talk, sort of comprehensively about fluids today, what we can do is just talk about some of the strategies. We'll start with water CO2, then we'll add a little complexity to that. But what are the strategies that people use within the context of the phase equilibria modeling packages that we've talked about? And so Doug and I have thought about this a little bit, and it seems that generally speaking, one of two n-member scenarios are employed for dealing with fluids in phase equilibria modeling. And typically these are the n-member scenarios that are easy to implement in the codes, not necessarily the scenarios that are most appropriate for the evolution of real rocks. And that's a slightly different discussion. So let's start by just talking about how folks generally would add fluid to their calculations. Method number one would typically be to fix the composition of the, if you like, the solid portion of the rock, the sodium, potassium, silicon, aluminum. So fix the ratios of those, but not the amount of the fluid forming components. And then make an assumption that that rock is in equilibrium with a fluid of known composition. So you force the rock into equilibrium, assuming that fluid is present. And in this diagram here, we show a fluid, which is pure water on the left, pure carbon dioxide on the right, can mix anywhere between the two. And these are sort of fairly familiar looking figures, temperatures going up here. And I think I sectioned this at 5 kilobars. In fact, this is a diagram that I showed earlier in the week when I was talking about perplex. And I made a comment then that the magnesite and the siderite I probably should have combined together into a single solid solution model, but I'd forgotten to when I did it. So that's the updated version of that. And so what we're seeing here is temperature. We're seeing fluid composition. We've made an assumption that the rock is always seeing that fluid, and we can look at the phase equilibria around here. We can, if we want to understand the system a little bit better, we can go into calculations like this and learn a lot by, I don't know, contouring the proportions of minerals as we go through here, or the compositions of those minerals perhaps. And so, for instance, this wedge here is where tremolite would be stable. The red here is lots of dolomite, decreasing to lower and lower dolomite contents with increasing temperature, and that's into this field here. And so that would be one way of handling these calculations, and it's a commonly utilized way of doing them. And calculations like this have a lot in common with this sort of thing. This is a mesh, a net of all of the end member reactions that might occur between, for instance, I don't know, the texts here, very small to see, but these are the end member dolomite, talc, quartz, tremolite, and a fluid. And diagrams like this will be familiar to many of you. This is actually rather similar to a diagram from Frank Spear's 1993 book, figure 12.3. And so this kind of shows us something about how the different end member reactions will depend upon the fluid composition, using a model for water carbon dioxide in fluid. This is not for constrained bulk rock composition, but if I jump back to the one that is, different pathways that a rock might take through this temperature compositional space might be used to simulate different processes. And Doug Tinkham will talk about that in a little more detail in a few minutes' time. But what we've shown here is temperature versus composition. We could section this, let's say at very low carbon dioxide content and at somewhat higher carbon dioxide content, and turn those into pressure temperature diagrams. This is unlabeled for obvious reasons, because it would get a bit of a mess, but this is a PT pseudosection drawn for, it's actually for a different rock composition than the last one, but it's for this composition of rock, pressure versus temperature, making the assumption that at every point on this map, fluid is in excess and the composition of that fluid is fixed, 99% water, 1% carbon dioxide. And we can look at the phase relations that we get out of this diagram, and we can, for instance, contour the amount of dolomite that one would get. Again, the labels on these contours are too small to see, but blue is not very much. Warmer colors, more and more dolomite stable. And so what we can do is we can resection this at different fluid compositions. So this is cut from a phase diagram. I basically recalculated this at a higher molar proportion carbon dioxide in the fluid, and we can see, as one might expect, the stability of dolomite increases to higher and higher temperature. So in a very simple case, this is the first strategy that we have available to us for dealing with fluids. We assume that a fluid is in excess everywhere in our diagram, be that a PX diagram, a TX diagram, a PT diagram, and we constrain the composition of that fluid. Now, there are implications that come with that assumption, and Doug will talk about those in a few minutes. We can expand that beyond just water and carbon dioxide, but it's convenient to show just water and carbon dioxide in this first case. So the second case would be that instead of constraining these components and then the composition of the fluid, we move these components up to here and we constrain the abundance of them in the calculation. And I'm going to pass over to Doug, who's going to talk a little bit more about that right now.
Okay, so thanks, Mark. That was a good introduction to that method. I want to share sort of a complementary method here, which is probably no better, probably a little bit less elegant, and it might be somewhat specific to Theriac Domino, but you could do this in any of the programs. You could fix the amount of each component in the rock, which is what Mark just said, but you could also fix the amount of the elements that go into your volatile components, hydrogen, carbon, if we're dealing with H2O, CO2 fluids. And you can, also let the calculation decide whether a fluid phase will be stable or not in that particular case. And I'll show an example of that. I think it's a little bit less elegant than method one. Method one there, Mark was, he showed a TX-CO2 diagram, and that XCO2 axis was actually fluid composition, where the program internally constrains the fluid of the composition of the fluid everywhere along the x-axis. It's actually very difficult to do that in Theriac Domino. You can fix the bulk composition of a fluid. You can fix the composition of the fluid, no problem in Theriac Domino, but you have to do that over the complete diagram, not vary it along the x-axis. So there's a way to do a diagram that's equivalent to a TX-CO2 fluid diagram. And the way you do that, and Cappy has shown this in previous short courses, is you add a significant amount of your fluid components. In other words, you add so much fluid that the bulk composition of the system basically controls exactly what that fluid composition would be. And I'll show an example of that. The other case there, labeled number 3, is you let the mineral phases and the phase equilibria directly control the composition of the fluid. And that would be more relevant to, say, a closed system where you're not letting fluid come into the system or even fluid escaping the system. And so let's have a look at those two particular cases. This is a diagram constructed in Theriac Domino using the Berman database. It's a TX-CO2 diagram. That CO2 on the x-axis is bulk system composition. It was not specified by fixing the bulk CO2, H2O content of the fluid, but of the entire system. In this case, I'm working in a very simple system. The composition here is 1 dolomite plus 1 calcite plus 1 quartz. If you look at the lower left diagram, 1 dolomite, 1 calcite plus quartz, but then we have 1,000 H2O. So this is, completely physically unreasonable. You simply have a few crystals floating around in a sea of fluid here. And on the right-hand side, you have 1,000 CO2s. And so your system is so dominated by H2O and CO2 that the fluid is a little bit variable composition along a vertical line, but it's essentially a fixed fluid composition along any vertical line here. Now, we've all seen these diagrams in our introductory petrology courses, and they're used to show the case of internal buffering of a fluid and external buffering of a fluid. And so, we can do these types of calculations here. And so I did this, taking this TX CO2 diagram, and we're looking at two cases here. In this case, I specified a fluid 50% H2O, 50% CO2. And basically by adjusting the system composition, we can make it an externally buffered fluid, in which case you just follow a vertical line on this diagram, or you have it internally buffered, where the mineral reactions occurring in the system will change the fluid composition. And what I show here on the right-hand side are the number of moles of the different minerals in these two end member cases. So internal buffering on the left and external buffering on the right. And so the way I do this is along this compositional binary, we start with just a little tiny bit of fluid in the system. And in this particular case, you will move up vertically until you hit that chemical reaction. Dolomite plus quartz goes to termalite plus calcite plus CO2, and you'll be generating CO2 in that devolatilization reaction. And if you only have just a little bit of fluid in your rock, then what will happen is, of course, the fraction of CO2 in your fluid phase will increase, and you'll follow that line. So this is the internal buffered case, which is sometimes easy to do, but sometimes not easy to do. The external buffering case is even easier. As I said, you just load up your system with mostly fluid, and you follow the vertical line. And you can see the differences in the mineral assemblages that's generated. Now, this is what's shown in our third year metamorphic petrology courses. It is very difficult at times, and I think when you get into more complicated systems, to do this, to sort of visualize the internal buffering path. So if you have a fairly complex system and you say, okay, I want to look at what happens to a fluid of a certain composition, you're going to have a little bit of trouble, because as soon as you start to run the calculation, so if you're interested in a fluid composition, about 50% H2O and CO2, as soon as you start to run the calculation, you'll find that that little bit of fluid that you put in the system there immediately reacts with the phases, and you might end up immediately with a drastically different fluid composition, which would represent the equilibrium fluid composition, which might be way over here. And so it becomes a little bit tricky at times to use these diagrams. You do need to play around a bit. Okay, so that's simple. I want to move into a little more complex, and I think one of the really exciting things in my mind in terms of metamorphic phase equilibria is sort of the marriage of more complicated fluid models with more complicated mineral models. A lot of the phase equilibrium we've been showing you is all in the presence of pure H2O. And we have fairly good thermodynamic data in many cases, not all cases. We can work in fairly large chemical systems, and we can look at a large range of rock types. But we're primarily doing that in the presence of pure H2O fluid. And so there's been some advances here in the fluids and in the databases. So in regards to the Holland and Powell database, Evans, Powell, and Holland added sulfides as well as some sulfur fluid species to the Holland and Powell database, dataset 5.5. There's a database out there called DS 5.5 uppercase S, where the uppercase S stands for sulfur, not to be confused with the database that has a lowercase s, which is for sapphire. And then they subsequently added, kept all those sulfide phases in the 2011 database. And there was also some new equation of states developed for the fluid phases. Holland and Powell 2003 developed a new COH fluid, and then Evans extended that in 2010 to include the COHS fluid. I think this is very interesting work. There has been some follow-up work on that, mostly done by Katie Evans herself. But this is really exciting because I think you can start to look at the interplay between iron, sulfur, and oxygen in a larger range of rock types, particularly rock types that might be you might more commonly see in ore deposit settings, where you might have a fair amount of sulfides kicking around, a fair amount of carbonate alteration kicking around, and you can start to investigate the interplay of fluids and mineral relations in these ore settings. So I think it's a very exciting area of research. And this is a figure from their paper from Evans Powell in 2010, which is a TX CO2 section. Now, in this case, the fluid was a pure H2O CO2 fluid phase, but they have sulfur phases on there. And so I've done some work on that, and we can almost reproduce the diagrams pretty perfectly in Theriac nominal. There's still some subtle differences, which I think are tied up in the activity models more than anything else. But the example on the left is the one that's calculated in thermocalc from Katie Evans' 2010 paper. And the one on the right is one I calculated in Theriac nominal relatively recently for the same bulk system composition. And I've just circled here some of the interesting relationships with which Katie points out in her paper here. If you look down there at high CO2 and low temperature, you can see your assemblages, dolomite, iron carbonate coexisting with pyrite, hematite, and anhydrite. It's a fairly oxidized system. And then you see as you go up to higher temperatures, pyrite, hematite, and anhydrite goes to pyrite, magnetite, and eventually makes sense. You ultimately move to pyrrhotite plus magnetite. And so these are interesting relationships to look at in some settings. And I think this is a really neat avenue of research for people to continue on. I'm going to finish up, so that, we can use the Evans, Powell, and Holland with the Holland Powell database in Theriac domino. It's a little bit tricky. It's not always perfectly numerically stable. I think it's a fairly complicated model. But, you can investigate the same type of systems in Perplex. And of course, you can do that in thermocalc. The original paper there by Evans and Powell was in thermocalc. These are diagrams that Mark calculated in Perplex. A very similar setup, TX CO2 diagram, calcium, iron, magnesium, silica, carbon, hydrogen, and oxygen system, it looks like. Some solid solutions there, some pure end members. And again, you can start to generate these pixel maps. And, these things don't take a long time to generate. And I think that that's one of the utilities of Perplex and Theriac domino, is you can really start to interrogate and investigate your rocks in a short matter to try to think about what is the phase equilibria telling you, where are the problems in the phase equilibria calculations, quickly determine whether or not your results physically make any sense or not. Because I think when you're working with these complex fluids, COHS, you can of course do some quite crazy things that aren't necessarily geologically reasonable. Now, this is another diagram that Mark calculated in Perplex, and this is quite nice because he's contouring the space for the concentration of different fluid components. So he's using COHS here, fluid, which you've been able to use in Perplex for quite a while. Jamie Connolly's had some COHS fluid algorithms in Perplex for quite a while. Looking at H2S, H2, H2O, CO2, carbon monoxide, and so forth. These are quite useful tools. We're not showing you anything state of the art here in terms of geological implications. What we're showing you is that these tools are available and they're ready for you to use to start to investigate these complex problems that you have to deal with. You need to use complex fluids to deal with. One of the really interesting things here is a recent paper. There's the Deep Earth Water Model by Sverjinsky in 2014, which extends the HKF equation state, I think, to higher pressure conditions. And we can start to look at aqueous species at quite high pressures now. You can do that today in Perplex. Connolly and Galvez published an algorithm. I think they call it the lagged speciation algorithm. And basically what it does is the fluid speciation algorithm iteratively communicates back and forth with the main phase equilibria solver until it comes up with that final lowest Gibbs free energy assemblage. And it lets you look quite complex fluids with lots of aqueous species in them. Something that's very useful when you're looking in high pressure settings such as subduction zones, but also be very relevant in many crustal settings. So I'm going to leave it at that, and we'll take some questions.
All right, great. Thanks so much, Doug and Mark. That was really good. It's something that I personally haven't dealt with that much, mixed volatile equilibria, and so it's great to see, yeah, all the different ways of getting at this. We had a few questions come in. So the first of these is, could volatiles and aqueous species affect the oxidation state of the rock and therefore lead to overestimating XFE3+ if they weren't considered? Doug or Mark here.
I think the answer is yes. Not sure how much the aqueous species will control it. There will be a little bit of a control there. I'm not quite certain how significant that control would be. But at the end of the day, when you want to investigate these problems with these complex fluids, you have to input a bulk composition. And to me, this is one of the hard things, is figuring out how much sulfur am I going to add to my system? How much oxygen am I going to have to add to my system? Sulfur occurs in various valent states. Iron occurs in various valent states. And so it's a fairly complex interaction there on, how much oxygen you add, how much sulfur you add. You can almost control the outcome yourself, depending on what bulk system composition you put in.
There's a really neat paper, I think it was last year, Katie Evans and colleagues, looking at how fluid generation during deserpentinization in subduction zone settings can mediate oxygen fugacity oxidation state in that environment. Really, really cool stuff. Well worth reading.
Okay, great. Thanks, guys. Next question. Is it possible to model fluid present systems where AH2O may be reduced? For example, how would we approximate the presence of salty fluids?
Well, if you could come up with an estimate of what the activity reduction is of H2O, and you're maybe not working over a huge PT range, in all the programs you can deal with this by either fixing the composition of the fluid or fixing the activity of the fluid. It's an approximation, because in reality, if you're going to model a system with equilibrium fluid over a range of PET conditions, the activity of H2O could change quite dramatically over a significant range of P and T. But if you have an independent estimate of what the reduced activity of H2O is in fluid phase, you can easily deal with that in all the programs by fixing the activity of H2O or fixing, say, the bulk composition of the fluid. You can do that in both Theriac Domino and Perplex, and I'm sure you can do it in thermocalc.
Okay, another question here from Matt. Is there a way to saturate a system in a buffering phase, e.g. graphite, at a specified FO2 buffer and calculate all reaction boundaries, etc.? He says he's sorry if he missed this. I didn't think this was exactly covered. I thought it's a worthwhile question. Well,
I know in Theriac Domino, you can specify buffers, nickel oxide, hematite, magnetite, graphite, oxygen, CO2 buffers. So basically, in Theriac Domino, you just come up with a reaction that involves O2, and you specify that on a statement called COM line, and then you add a star to turn it into a buffer. And what that does is that any P and T, if you have that buffer active, it'll use that equilibria to constrain the chemical potential of O2, and it'll fix that chemical potential of O2 in your system, so that when you do the rest of the Gibbs minimization, the chemical potential of O2 is fixed by that particular buffer. And so you can set it up for graphite and iron oxides.
That would be a somewhat less straightforward operation in Perplex than it would in Theriac Domino. Also wanted to mention, there was a question about complex fluids and oxidation states. Should shout out to Jesse Walters and colleagues' 2020 paper, where they model fractionation of sulfur-bearing fluids and the impact on ferrous ion ratios of the residuum, suggesting that the effects can be quite large. Should have shouted that out earlier.
Okay, great. Yeah, no, thanks for bringing that up, Mark. 1 second, let me just look at my next. Another question here: do any of the all the melt models incorporate just H2O, or do they include other species?
I'm not aware of any of the Holland and Powell melt models incorporating other species. I mean, the solubility of carbon dioxide, for instance, in melts, as Dave Waters was saying, is somewhat lower, well, substantially lower than water. The melts and P-melts programs, I'm not so sure about. The kind of the mantle melting models, I think they do incorporate more complex sort of carbon-bearing species, but I'm not aware of any of the models that we've been talking about so far in this workshop. Doug, anything to add?
I think you can in melts, but I'm not. That's one of the programs I haven't used much, so I don't know the details.
Okay, great. Thanks so much, guys. Again, you just talked about the buffers. Someone asking, does the buffer you use influence the other phase relationships in Domino when you set one of these buffers in your comm line, as you were saying, Doug?
Well, yes. Yes, it does. I mean, if you don't specify the buffer, then, you know, when you calculate the Gibbs free energy minimum and the equilibrium assemblage, you know, that equilibrium assemblage, the compositions of those phases, it dictates the chemical potential of O2. Now, as you go throughout your diagram, that, you know, the fugacity of O2 or the chemical potential of O2, you know, varies quite a bit. So, you know, we're all just letting the equilibrium, the bulk composition and the equilibrium assemblage control our oxygen fugacity in most cases. When you specify a buffer, it's like, okay, I'm not going to let the main assemblage dictate what the chemical potential of O2 is. It says, oh, I'm going to use this little equilibrium between hematite, magnetite, and O2. And at every P&T, I'm going to calculate the chemical potential of O2 from that equilibrium. And that will have an effect on your assemblage that you calculate.
Okay, great. I think that answers that.
Particularly mineral, I've seen, particularly in the fluids. So I've done some work where I'm using buffers when I'm using, you know, COHS fluid in it, and it will control to some degree what fluid composition you'll get.
Okay, another question we've had, a couple of people asking here, is it possible to do phase equilibrium modeling for rocks that have been extremely metasomatized, and how you'd approach that? I suppose it's slightly different to your mixed volatile equilibria, a bit tangential.
I think to some extent, it depends when the metasomatism was occurring. If the metasomatism was occurring and the changing composition was occurring at the PT stages we were interested in modeling, then we really shouldn't obviously be thinking about a fixed bulk composition at all. And then we really need to start thinking about how do we do, you know, fluid infiltration, fluid loss, and true reactive transport modeling, which is complex. And so it's pretty easy right now to add water to a rock, to add carbon dioxide to a rock, to add something between the two. But to add all of the components that might be dissolved in those fluids is still a challenge. And so that last slide that Doug showed with the extension of the Helgsen-Kirkham Flowers model, the deep earth water model, which allows us to begin to calculate sort of the solute species, that opens the door for us to be able to look at this in a more quantitative way. But I think we're still some way short of that being a sort of a routine calculation that we can all just do just like that.